All right. Hello, biology people. I hope you're doing well today. Here to get into the idea of bonding, chemical bonding. So up to this point, you should be very familiar with the periodic table. You should be able to navigate through that pretty well, pretty easily. We should be able to understand the rules of 2, 8, and 8, valence capacity rules that achieve stability for the atoms, right? So with that, this next little discussion will deal with different ways, different chemical bonds that can happen that will enable the atoms to become stable. And in chemistry, that's how you kind of win the game of chemistry. You become stable. So there's different strategies to accomplish that. And one of those is the idea of oxidation. Another is the idea of reduction. So these are chemistry terms. I think sometimes they're a little bit complex, but oxidation is defined as the loss, getting rid of, kicking out, the loss of a valence electron. And reduction seems kind of backwards, but reduction then is the gaining of a valence electron. So oxidation to lose valence electrons, reduction to gain valence electrons. And by doing that, that would then help the atoms achieve their maximum capacity of electrons. So again, this happens often in chemistry and has relevance to biology. So whenever atoms lose or gain electrons, we no longer call them just atoms, right? They become chemically unbalanced. They have the same number of protons. Proton numbers don't change, but we can lose or gain electrons, and that causes then the idea of ions. So an ion is, it happens when we lose or gain electrons, when we undergo oxidation or reduction. Right? And the same atom typically won't undergo both, right? The same atom or one particular atom typically undergoes oxidation. A different type of atom tends to undergo reduction. Right? That's normally how it works, unless they're part of like a redox chain, as we call it, reduction oxidation chain. And I think you have a simulation, a Lapture simulation that kind of addresses this a little bit. So atoms can be reduced for a little while and then they can oxidize. So that does happen occasionally, well, often in certain chemical pathways. So we're going to give these things special titles now, right? So if we happen to gain an electron, so if we see the idea of reduction, these might be flip-flopped in your notes. I don't remember which sequence I gave you in the notes, but I'm going to start alphabetically. So ion first, and then we'll get to cation. But an anion is due to reduction. So we're gaining an electron, and that is giving us an overall negative charge. So we're reducing the overall positivity. So that's why they call it reduction. But we gain an electron, we gain a negative charge, and we call that anion, right? An anion. It's an ion, a charged ion, a charged element, charged atom with a negative, right? A negative ion, anion. A cation, right? If you see the letter T, cation is like a little plus. A cation is a positive charge that is due to the process of oxidation. So the loss of electrons, we're losing negatives, but we have the same number of positives, so we have that net charge of positive. So think of this little cat here, right? Cat, right, with the positive, all positively charged there, a cation. So when we undergo the idea of oxidation again, so oxidation is going to be down here. Oxidation is going to help us to form cations. So this is a complete loss of a valence electron. The atom didn't mess, we don't ever lose protons. So its proton stays the same, but we're losing electrons. So we end up with more positive charges than negative charges. So oxidation. Reduction, the opposite. We're going to keep the number of protons the same, but we gain more and more and more negative charges. So that gives us an overall negative charge. So a negative ion, anion, right? So that's where they get those terms from there. Now in chemistry, they talk about cations and anions. In biology, we don't typically use those words, but we deal with those cations and anions. In biology, we tend to use the terms electrolytes. You know that if the baby's sick, you know, diarrhea, whatever, we give them Pedialyte, right? It helps to reinfuse all of the electrolytes that they're losing. If you play sports, you're out there running, playing basketball, or running a 5K or whatever, you're sweating a lot of your electrolytes out, so you have to replenish them with Gatorade or Powerade or different sports drinks. All of these, sodium with a positive charge, magnesium double positive, calcium double positive, chlorine negative, anything with a little charge, we know is going to be a type of ion. And normally these ions are safe for the body. Right? They're safe because they are already stable. So they have stabilized. It lost that lonely electron out in that valence shell. So it lost something to become stable. So these are important, safe, necessary types of ions in the human body. So I hope that's making sense, right? The idea of oxidation and reduction. Now we get into an idea of bonding, right? And there's 3 different bonds we're going to cover: the ionic bond, the covalent bond, and the hydrogen bond. Let's start here, just because we're already talking about ions. So let's look at the idea of the ionic bond. And I'll come back to this. I'll show you what it looks like, then we'll come back and analyze here. So we're going to look at the idea of sodium and chlorine. Right? Sodium and chlorine remind me of humans. Maybe you know people like this, that this individual is just toxic, right? They're toxic, and they need to fix themselves. They need to work on themselves before they go into a relationship, because if they bring that toxicity into a relationship, they're not going to do well, right? So I wish people would learn from these elements, and I wish they would behave kind of sometimes like these ions that participate in ionic bonds. So we have a toxic sodium and a toxic chlorine. Ew, both toxic, both, it would be a terrible couple if they bonded together. But something happens first. So sodium decides, you know what, man, I gotta fix me first, right? So I'm not gonna be a good partner unless I address myself first. So sodium has that lonely electron. So sodium woke up this morning. Oh man, I'm gonna have to go work hard for 7 more electrons. So I can end up with 8 for that third shell. Or I have that one lone electron just kind of causing me problems. I can get rid of that one. So that's what sodium elects to do, right? Sodium is going to elect to undergo oxidation, to lose that one. And chlorine is in a different situation. Chlorine woke up this morning toxic, but saying, you know what, man, I'm close to being stable. I just need to go out and find 1, or I can give up 7. But that's a lot, right? So that's a lot of electrons to give up, to oxidize, to go to an earlier shell. So chlorine decides it's worth the effort to go work hard for 1 electron. Sodium decides it's not worth the effort to go try to gain 7. I'm just going to lose 1. That's easier. So in this process, we have the oxidation of sodium. So you see sodium has no charge. Once we lose that electron, sodium drops to a positive charge, right? Because we lost an electron. So that has to happen first, and it happens on itself. So sodium oxidizes, sodium becomes stable on its own, right? So that electron's out in the universe somewhere, right? So now chlorine goes and works hard and finds that electron, right? So that electron is now brought into chlorine's valence. So we can no longer just call it chlorine. We have to call it chlorine with a negative charge. So chlorine stabilized itself. So dun, 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 dun. Now chlorine is stable, sodium is stable, and now they're ready to participate in an ionic bond. So we talked about this in an earlier discussion. Once we have opposite charges, so law from physics, opposite charges will attract. So the positive charge does attract to the negative charge. So again, stable, okay. Well, let me back up. It's not stable because it's still showing the regular atomic form, right? So undergoes oxidation to become stable and a positive charge. Chlorine undergoes reduction to become the chlorine anion, stable with a negative charge. And now the laws of physics apply, and these opposite charged particles kind of attract together. And this attractive force is what we call the ionic bond, right? So ionic bond, a couple of things have to happen first. Oxidation on one element, reduction on a separate element. Once we have charges and stabilization, then they attract to form the ionic bond, which is sort of here outside of the two atoms. So hopefully this definition makes sense, right? So ionic bond involves a complete transfer of one or more electrons. So first, we have to have one atom that is oxidized, and then a separate atom that undergoes reduction, the complete transfer of electrons. They generate electrical charges, opposite electrical charges, and then they're able to bond together. So form an electrical attraction between cation and anion, positive and negative. So this is basically how your refrigerator magnets work at home, how magnets are drawn together. It's not too hard to pull the magnet off the fridge. So we say, well, it's not a strong bond, but it is a bond, right? We do have stability, and we do have then this attractive force. And what bonds allow us to form now is more complexity, right? It allows us to form molecules. So we went from the atom, the different types of atoms that we call the elements. And now when elements start interacting together, we have what we call a molecule. So the molecules are two or more atoms that are bonded together. So one thing I want you to understand on the ionic bonds, right? The bond happens after we gain stability. So first, stability had to be achieved. And then the bond kind of naturally happens. And again, this works very, very effectively in human systems, right? So in humans, once two individuals are, they're okay with themselves, they're functional on their own, they're not necessarily dependent, codependent. They typically find people in that healthy state of mind, right? And that's what these atoms do here. So they fix themselves first, and then they enter the bond. So the bond is not used to stabilize the individual atoms. So that's going to be different from this next one here, right? So ionic bonds, just showing you how we get these salt crystals where we have positives and negatives interacting together. So they orient themselves in a way where they're most in contact with the opposite charged ion there, right? And once we eat salt, salt is broken up in our body, and it's okay, right? It's okay because if sodium is not attached to chloride, it's okay. It's okay because they're stable. This is a stable element, stable ion. They don't need to be in the bond to be stable. They contribute then as electrolytes for our body. So this is, again, a good practice little situation for you to get practice on the definitions. What is just a regular atom, and how does that atom differ from a cation? What is a regular atom? How does that atom differ from anion? How do the number of electrons and number of protons interact as well here, right? So I'm going to ask you to solve this, figure out this. The next slide I have the answers, but don't copy the answers, right? So see if you can generate this on your own and see if it's matching up with the correct answers there. So with that, I'm going to stop this video that addresses the ionic bonds, and then you'll get the other video on covalent and then on hydrogen bonds. Stop that here.